Good afternoon, everybody. My name is Blake Blaze. I was an intelligence officer in the Navy for 5 years, so timeliness is very important to me. I was just looking at my watch, counting down to exactly 3:30. Thank you all for joining us. I'm joined here today by Dr. Aaron Reedy, who spent 7 years as a high school biology teacher in Chicago Public Schools before pursuing a PhD in evolutionary biology at UVA, and then eventually founding DataClassroom. We're also joined by Dr. Reedy and Schultheis, who is currently the Education and Outreach Coordinator for the Long-Term Ecological Research Program at the Kellogg Biological Station. Before that, she completed her PhD in plant biology at Michigan State's Kellogg Biological Station, and is also the co-founder of Data Nuggets.
Yeah, thanks for that introduction, Blake. And I just want to make a note to people who are here or who are just joining us. We're going to go through some data sets, and we're going to actually spend some time analyzing data with data sets that we think are good examples for you to work with your students. If you want to follow along with us today, you can create a free account at dataclassroom.com. If you don't already have one, you can sign up for the free account and you will be able to follow along. And at different times during our hour together, Blake will drop the web addresses of the data sets into the chat. So he'll be able to get you onto the same pages we're sharing, so you'll be able to follow along with us as we go.
Thank you very much, and I'll do my best to make sure we get to all the questions addressed in the chat. And if you have any questions we don't get to, we'll follow up offline afterwards.
Excellent, excellent. So Liz, you ready to do this?
Yep, sounds good.
Okay.
I've got 2 dogs in my room, so I'm always going to be on mute unless otherwise.
So if we hear barking, we'll know where that came from. Just by way of introduction too, I like to show this photo at the beginning of webinars when I present in a data classroom capacity, just to show you where I'm coming from and where a lot of these ideas and motivations are coming from. Is my own classroom in the Chicago Public Schools. I think data classroom is very different than a lot of educational technologies, because we really stemmed from a classroom environment in a way that I think a lot of big companies haven't. And I think it helps with helps us better able to make things that help you all out. So just as an outline for today, we're going to do a little welcome and introductory discussion, talk about some difficulties you might have in teaching about big problems, and specifically climate change. And then we're going to get into 3 different example data sets that you can use in your teaching. And Liz and I put our heads together for this, and we actually have a lot more than just 3 data sets that you could use to teach climate change. And we will include those in the workshop follow-up materials. So if you have registered, you will get those emailed to you within a week. But the 3 we're going to talk about some data that comes from mynasadata.com, and it's temperature data that NASA's been collecting and gotten a hold of going as far back as 1880. We're going to be talking about the Kyoto cherry tree data set, which actually goes back all the way to AD 812. So that's the year 812, 1200 years of data there. And then we're going to be talking about a data set that's in the springing forward data nugget, which Liz is very familiar with, and we'll go through those things. So with that, Blake, you just want to kick off our discussion portion?
I do. First question I have for the 2 of you. So why are we hosting this Big Problems 4-part workshop series?
That's a good question. Well, one of the reasons I think I was interested in doing this is I'm always really interested when I'm working with students on conveying the how we know what we know. I think it just comes from me being a really skeptical person by nature, that a lot of times in my own education, I just wanted to know, how do we know that? How do we know that fact in a textbook? And so I think that's what we're doing with this Big Problems series, is we're going to take issues like climate change, like mass extinction, global health issues, and we're going to look at data that informs the facts as we know them in these very big arenas. So for me, I was interested in doing that as just kind of an extension of that.
I think it's really important you're tackling these kind of issues, and not just by talking about them, but by having students get the opportunity to work with real data surrounding these issues, because it can show them how to handle other things that come up in their life as well. That, you know, if you want to know the answer to something, the data is probably out there, and you don't have to trust the interpretation that other people give you. You can actually go out and get the data yourself and answer questions on your own. So I think, you know, climate change and all the other topics that you have coming up are important, but this is something that we can model for students to tackle with any question that they get curious about in their own lives.
Yeah, I think you know, another part of this is just because students really care about real issues. So any time that you can find a way to bring in a major problem that is something that students actually care about, it's, you know, it's important to do that, and it can be extra motivation for things. So I know, like, for example, I just want to point out that I know, Blake, other people might not know this, but I know that you care very deeply about climate change. And I think a lot of teachers in our audience do too. If those of you aren't aware, Blake actually runs World, and you can check out itsworld.com, and the link to that is actually going to be in the slides here. But they're focused on climate science and climate science learning for younger kids. And so, Blake, I know this is something you care about too.
Yeah, very near and dear to my heart. And there's a lot you're saying about the kind of need for students to answer questions on their own, that the data is out there, and scientific literacy is so important, especially in an age of misinformation, when a lot of things online can prove things without referring to data. And so giving students that fluency and comfort with numbers is so important.
Mm-hmm.
So some of the things we talked about in meetings leading up to this, I think, from this question, but what are some of the difficulties in teaching climate change and other kind of real world topics or socio-scientific topics?
Liz, you want to go first?
Well, I was just thinking of a difficulty that surrounds any time you're using authentic data in the classroom, that there are a ton of data sets out there, but they're not necessarily in forms that are really easy to use. And so Aaron and I were just talking before this about all the work he put into some of these data sets to get them in a form that's usable for students. So hopefully we're presenting data sets in a way that make them something that you can just take and use in your classroom. And then that once you've seen that process modeled, potentially students can go out and do that on their own when they go hunt for data. But if you have to do that every time you want to answer a question, it's going to be a little intimidating to go through all these data literacy steps over and over again. But having a mix of materials that are just ready to use in the classroom, and then also challenge students to go out and find their own data, it's a good pairing.
It's the ugly truth of the insights of data science, is that, like, you spend so much more time formatting data, and then, you know, a lot of times it's just impractical to get to for a student who wants to direct their own learning. And that's why I think teachers find data sets that are curated so I mean, that's why Data Nuggets has been able to grow the way that it has over the last decade, because you all have great data sets and you've done that work to get people ready to work with them.
Yeah,
right
and it's a good mix. Like, you don't want to do all that. You don't want to always curate data perfectly for your students, so it ends up being sort of this like prepackaged thing that students are used to. So kind of giving them different levels of challenge with data sets, I think, is a good pairing.
Yeah. There's the dog. One of the other things is that that's difficult about teaching a topic like climate change is that it involves models, and it involves probability, and it involves, you know, a high degree of uncertainty in any one measurement. So you have to look at trends, and you have to look at a lot of data. And so there's lots of times when, you know, students aren't equipped necessarily with the background in probability and statistics. So teachers, I think a lot of times, I know I always felt this way, is like, you have a ton of work to do in backfilling that information. And there's like just a lot of prep you've got to get to sometimes before you can just launch into data and interpreting it. And so that makes things tough. And then another thing, you know, I think it's at least bears, you know, it's worth mentioning that for whatever reason, climate change has become a political topic in our country too. And you know, some teachers can, I certainly understand this, want to just kind of veer away and avoid topics that, you know, could potentially make parents mad. So it's, you know, we would be disingenuous if we didn't acknowledge that that's also a reality that teachers are facing out there.
Yeah, I think it could be intimidating to go into a lesson where you think, I don't know everything about this topic and it's controversial. So, you know, it might be too scary to broach in the classroom. But like, as a scientist, I always try to model the fact that, you know, scientists don't know the answer to all the questions they set out to answer. They don't know what a particular data set is going to tell them before they analyze it. So that's I think a good way to model a scary topic potentially is just, let's see what the data tells us. Like, the teacher didn't make the data set, it's real data, it's actually showing a true trend. And so, you know, if you're looking at a real set of data, that is a good way to broach a subject, I think.
For sure, for sure.
So I just went and dropped the data set that we'll be looking at first in the chat. Feel free to follow along as we go through these. I think that's probably the best way to generate questions, but also feel free just to watch and then drop questions in the chat and we'll try to answer them in real time.
Okay, so if you've been to dataclassroom.com and you've created a free account, then when you click on that link Blake shared with you, you'll go straight into here. You'll be right into this data set. If you haven't, you'll need to sign up, and then you'll be able to log in, and that link will work for you to get here. This data set is one that I'm really excited about. It's a collaboration with My NASA Data that's in the early stages, and mynasadata.com has just a huge amount of data that NASA has been compiling and collecting for a long time. And it's a really amazing wealth of data resources. And what we did for this data set is we explored one particular question, and we grabbed a small subset of this just massive amount of data that's out there. And I did a bit of reformatting too, because the NASA data was recorded monthly, and I moved this into yearly averages. So I did a little bit of formatting. So what you have in this data set is data going back to 1891, and each row in the data set is a different year's worth of data. And the main variable that we're looking at is this average temperature anomaly. And this is how much above or below an annual average temperature was above or below the 1951 to 1980 average temperature. So this block that's in the middle, a little bit closer to the present than the true midpoint of the data, and just seeing, you know, how much above or below what those average value these data are. So I'm gonna jump over to the graph tab, and DataClassroom does have some built-in help with the graph wizard, but I'm just going to go right into the graph tab and start working on this. Actually, before I go right into the graph tab, we're going to come back here. But before I do that, I also want to show you that there's an assignment that goes with this. So there's table, graph, and assignment, and we can send out an answer key to this in the follow-up materials too. But this activity is called Feeling the Heat. What can NASA data tell us about the ice albedo effect and climate change? And we've got a series of questions here with some background. So first, let me give one piece of background if you're not familiar with this. But the ice albedo effect is basically this idea that as the area of the Earth's surface that's covered with snow or ice melts, there's going to be a dramatic difference in the amount of solar radiation that is reflected back to space off of that snow. And as that snow melts, more of that solar radiation is going to be absorbed by the Earth, and those areas are going to warm faster, and faster as compared to areas that never have snow cover. Like if you think of low latitude areas like the tropics, they don't have any snow. So, you know, as they might be warming, but we don't expect melting snow to affect that. So the big hypothesis for the ice albedo effect is that high latitude areas that are covered by snow are going to warm faster than the rest of the Earth as that snow melts. And that's called the ice albedo effect. And so you need to keep that in mind as we're is we're looking at this data set, and we're going to look at these 3 key variables, this average temperature anomaly in degrees Celsius. And again, that's the amount above or below this average temperature from 1951 to 1980. We're going to look at the year, and we're going to look at the latitude zone. And I've coded these into high, middle, or low. So this is a categorical variable now. High latitude is 60 to 90 degrees of latitude. Middle is 59 to 30 degrees. And low is 29 to 29, so spanning the equator on that part of the Earth. And we have these activity questions. So what I want to do is actually just kind of go through and break down these questions and show you graphically how your students would analyze this. And now, Liz and Blake, I've been through this and I've done this analysis a number of times. So please ask questions that you have as a naive or close to naive viewer of this analysis. So
I had a question just about that. We're comparing every year to a 30-year average. Did they kind of give an explanation of where that 30-year, how they chose that year range for the 30-year average, and then why 30 years too?
Yeah, no, they didn't. I can speculate on that. I don't actually know, but next time I talk to Brad at NASA, which should be in a week, I will ask him that question. But I think they chose a long enough time span to account for that year-to-year variation that you'd expect with annual temperatures. And so I think 30 years, but then again, I think they also didn't want to choose too big of a chunk of the total area that they were, comparing against, or the total time span. So I think it's reasonably big enough to get an average. And then they chose something, I think, sort of toward the middle, because you'll see if there's a trend, and spoiler alert, there is a trend in the temperature over time. But if you were to choose something right at the beginning or right at the end, you'd be misleading in 2 different directions. So I think they chose something kind of close to the middle with a big enough time period that they can take a meaningful average. So the first question is, what is the variation in temperature from year to year as you compare different latitudes, low, middle, and high? So I'm going to go to the graphing tab, and I'm going to select this average annual temperature anomaly variable, and I'm going to plot that. So each data point is a different site and a different year. So it's each year times 3 sites minus points for missing data in there. Because this the data set started in 1880, there's some missing data points. And I've gone through and pruned out those rows that had missing data before I uploaded here. So it's not exactly 1 point per location per year. When we split this out by latitude zone, so I'm just going up to the column header for latitude zone, and I add that on my x-axis. So we can see high latitude, middle latitude, low latitude. And when we're talking about variation, what do you notice here right away?
I'm shocked at how much more variable the high latitude areas are. It's crazy.
Yeah, those annual temperature swings are a lot bigger. And if you think about this sort of makes sense even if you think about just the temperature within a single year. Now, each of these data points do represent a year. But when you think about this, the tropics, they don't change temperature very much summer to winter, if they even really have a true summer or winter, right? It's just it's more of a stable temperature. And as you move further away from the equator and closer to the poles, you get bigger swings in temperature, month to month and day to day. And we see the same pattern year to year. You get much bigger swings. Yeah.
I like this data set too, because it's actually, the variability is the interesting part of the data set, where usually, students might go right to calculating an average for something and they'd be missing the cool part of the story, which is about variability. So it's a cool, if you're, wanting to do a lesson on variability and emphasize that as an important metric, this would be a really cool data set.
And yeah, and great point. Variability is so important, and it frequently gets the short shift. We talk about descriptive measures such as like means and medians all the time in grade 6 to 12 and even in a university. But variation, that can tell a really interesting story.
It's also great too, because you don't need to calculate anything to see it. And so a lot of times I've heard teachers will just talk about range. So just even having students look at the highest and lowest data point in the cloud, like you can get into more descriptive statistics about it, but it's pretty clear, just with using your eyes, you can see this trend, which is cool.
Yeah. And we'll get on to the next question, but just for the sake of just sort of like just demoing the resource just a little bit here, I'm just going to copy this graph and show you, how you could use it to answer a question in this assignment. So if I go back to the assignment tab, this graph is part of the answer to question 1, and it even instructed students to make the graph. So if I click the edit there, it's going to open up a copy of this in Google Docs, and I'm going to go down to that question. I'm waiting for Google to catch up here, and I'm going to go down to the question here where it was asking about variation in temperature from year to year, and asking your student to answer that. And I'm going to paste in the graph here. Google's still catching up with me. Even though I am the creator of a web app, I frequently am frustrated with web apps. But there, so actually I did it twice because I couldn't stop clicking the buttons. But you can see here's how your students can add in a graph and then write in an explanation. And when we go back to that DataClassroom tab, you can see when it will auto-update every 2 minutes. But you can see if I do this reload, it will bring in the answer, and so students can paste in their answers or their graphs right into that data sheet. So I'm not going to do that every time. I just wanted to show you, how they could take those graphs and actually work on the assignment. And sorry, I just clicked out of this. I've got to get control of my computer screen back here. Hold on one second.
Would you mind going back quickly to the graph? I think just since different of our attendees today have different lag on their video, could you just show the quick edit function again?
Yeah, the quick, sorry. Oh, on the assignment. So what I did is I go over to the assignment, and I will say, when you go, I'm the owner of this data set. So all I have to do to start editing it here is click this pencil that says edit, and then it opened me right to the Google Doc here. If you are using this data set, when you go to click edit, it will say you need to save this data set first. You save your own copy of it. Then when you click edit, you'll open up your own Google Doc and you'll start working in it. So you don't have any power to change the original that all 60,000 DataClassroom users can see, but you can make your own copy of it and do whatever you want to it there.
And if teachers want their student responses, can students just send them that Google Doc link to share their responses with the teacher?
They can, and students can they can click the edit button, save their version of the data set with their answers in it, and then turn that Google Doc into their teachers, however they're used to turning in digital materials. I don't know that there's a standard quite yet for how people turn in digital materials. A lot of that changed in the past, year and a half, but that's students would have that ability to use that as an answer sheet as well.
That's awesome.
Yeah. So I'm going to go back away from the assignment tab and back to the graph tab. And the next question in this assignment is asking just, what's the overall trend in these temperature anomalies over time? So what I'm going to do is I'm going to add year to the right of the graph. So I go over to the column header of year up here, and I click show. And now it's added on the right. And if I want to put year on X instead of latitude zone, I just click X for year, and I put year on there. And unfortunately, this is a pretty clear trend, and not one that should make you happy to see, because I can fit a regression line to this, and this is a clear upward trend with a very robust and very large data set sampled from 9 different locations, 3 different latitude zones. This is a pretty clear trend toward a warming planet. It's highly statistically significant. If I wanted to see that, I could open up this graph-driven hypothesis test, and I could run the linear regression. You get a p-value of less than 0.01, which is as low as our display goes. I actually suspect that's probably a few more decimal places smaller than that. But this if you got our help on interpreting this relationship, is there a relationship between the values of temperature anomaly and year? And yeah, there is a significant relationship between temperature anomaly and year based on this data set. And so this is sort of the next question in that data set. But remember, we're also interested in that ice albedo effect and how different latitudes might be warming. And we can't see any of that here.
Aaron, that's a very clear trend. One thing I'm interested in, can you also analyze side by side the latitude and the time, change over time?
The latitude and the
I
change.
want to see a visual kind of representation of how it's changed over time for each of the latitudes. Could we break that out too?
We can, and that's exactly where we're going next. And we'll do it in a single graph, but we'll break it out by taking latitude zone over here on the control panel at the right and clicking Z. And so you'll see it lights up red. And now what we've got is we've split out each of those categorical variables. So we've told the computer to group them by a third variable, which we call Z, and it's grouping by latitude zone. And so you can see in low latitude close to the equator in orange, then you see middle latitude in green, and you see high latitude in blue. And this kind of blew me away when I saw this at first, because I've read a number of things in the popular press about the ice albedo effect and the warming of high latitude areas on planet Earth. But for me to just be able to go into this massive data set on NASA and just pick a couple of sample locations and to plop it in and to see the trend so strong here, it really blew me away.
And Aaron, sorry to ask you to do this again. Would you mind? Can we run a test like we did in that first display on the data as it's displayed now?
Run a test on
the graph-driven tests.
So unfortunately, we're bumping into one limitation with DataClassroom there. It will only do a single linear regression at a time. However, I could, if I wanted to, run a test for just the high latitude zone, say, for example, or any of those. I can go up to latitude zone here. And this is a great way to analyze this data set. And I could exclude low latitude and middle latitude. And I just check those exclude. And now I've just got high latitude on the display. And if I run the graph-driven test, it's going to run that. And it's actually not considering any of the other data points. It's only looking at the high latitude data points because the others are excluded. So in that way, and if I wanted to do that for a single zone, I could go back and maybe I'll exclude high because it looked quite a bit different than the other two. The other two looked really similar. If I leave them in, and I'll get rid of the group by Z, so this is truly representative of what we're going to test. And we test this relationship here with a linear regression. This is still highly statistically significant. It's just a different slope. Now there is a statistical analysis to test if one slope is different from the other. That kind of regression model is currently not run in DataClassroom because our target audience is grades 6 to 12. But if there are some university teachers in the audience, we are getting very close to releasing DataClassroom U, which is going to have more advanced analytical capabilities, including the ability to look for a treatment by measurement interaction. So you can compare multiple slopes at once with DataClassroom U, but not with this current version. I'll put that all back. But yeah, it blew me away. And looking at this, and hopefully your students would be able to see this too, that when you look at all those lines, you can really see that across all locations, the temperature anomalies that are positive seem to be increasing, and at high latitudes they're increasing much more dramatically than they are at low and middle latitudes. So this is exactly the kind of data we would expect to support the ice albedo effect.
Very cool. And Aaron, if students in the same classroom were kind of looking at this problem, or this assignment, what ways would individual students be able to customize or change the display of the data to kind of fit what the story they were trying to tell?
Yeah, so they can customize the display of the data in a lot of different ways. So if they open up I think this is what your question is getting at. If you open up the display, you can change colors and font sizes and scale of the axes and all these kinds of things. You can do fun stuff. I always love to show this too, because you could represent data points with emojis instead of dots, and I'll make those a little bit bigger so you can actually see those. And I didn't know you were going to ask me that question, but I was just playing around with this, and I went with the hot face emoji. So these, this is the hot face emoji. So you can play around with that, and you can customize really every aspect of the visual before you present it somewhere. Did that answer the question?
Yes, yeah, and you already kind of showed by virtue of being able to show different variables, but just it's interesting that students can change the jitter or the length of the axes, because sometimes displaying the data communicates a story more clearly.
Yeah.
Yeah, I've heard from teachers using this, that basically being able to customize the graph really gets student buy-in on it, that like a lot of students have some artistic skills and want to take ownership of the graph. So they, if you're more artistically minded, you can really play around with it and make it attractive, and not only attractive, but better able to communicate the story you're telling. So
yeah, for sure. That's always fun. I know as a working scientist, like I always love the figure making part, where you get to decide like, how are you going to show the world the story in a picture. It's a really fun aspect of working with data. So unless there's any more questions on this particular data set, I think we could go into another example. Blake, were there any questions from the chat that are sort of relevant to this?
No outstanding questions for now.
Okay, so let me go. I'm going to just go to the browse tab. I'm going to leave this. I don't need to save any changes here. And I am going to go to this Kyoto cherry tree blossom dates data set. And so let me just give a little background. And this data set is much more raw. There is not a pre-made activity or anything for it yet, but we will be adding something eventually. Blake has actually started some work on this already. But this is just a data set your students can work with. This may have gotten or you may have heard about this data set in the popular press recently, back in March, because they've been keeping track of when peak blossom is in Kyoto, Japan for their cherry trees. They've been recording this with reliable records going back to the year 812. So that's not 1812, but 812. And they loosely define that as the time point when 70% of the cherry blossoms are open. So this is sort of, what is the day of the year when there were the most cherry blossoms on these trees? And we've converted these dates into day of the year. So like January 1st is day one, and then it just the days go sequentially. So we've converted this into a numeric variable. And so to kind of show how you could analyze this, I'm gonna jump to the graph tab, and I've already got this one done where I've plotted year on the x-axis and full flowering date on the y. Right, so the earlier in the year that the flowers opened, it's a lower data point in that field of points, and the later in the year, you see a higher point. And you can look for a trend in this. And when you look at a regression line, it looks like a slight trend toward an earlier date. But to get the interesting part of this, you just have to kind of look kind of carefully, and we can do some things visually to look. What do you notice about this when you on first glance? And Liz, I know you looked at this data set before, but what did you tell me after the first time you saw the data like this?
Yeah, so I knew that this was a really popular data set, or a famous data set, to show a shift in timing of plant flowering over time. So you could connect this data set to a phenology lesson, where you're talking about how are plants responding to the climate change we just saw in that previous data set. Do plants actually care that the world is getting warmer, that things are becoming more variable? So when I first opened the data set, I was shocked that with such a long time period, it doesn't look like that strong of a trend. So it does appear that plants are flowering a little earlier over time. The slope is slightly negative, but I kind of expected it to be a little stronger than that.
Yeah, and I had pretty much the same experience in seeing this. And then, but there's another way to look at this, and this is how the researchers who published the paper, where these data come from. If we add time period on there, and we do the same thing we did with the last data set, where we split that out, And the two time periods that we've added to this are pre-industrialization and post-industrialization. So we used 1850 as a cutoff. This is largely when use of burning coal to power steam engines really exploded and became a very, very well established thing. And when we look at the last bit of this from 1850 to present, the data look a lot different. But even here, it doesn't look as different as I might expect. But when you,
Yeah, I think this is a good point to stop with students and like have them think about the biology or the science behind a data set, because you can just start clicking around in a giant data set and do some really powerful stuff. But if you don't really understand the data you're looking at, like I didn't when I first opened this, I'm used to looking at data sets for phenology that are only after the Industrial Revolution. So usually you don't have data that go back this far. And so I was kind of treating it like data where I'm looking at it all from this like one period of time, pretty recent history. So it's, yeah, stop and have a conversation with students like, when was the Industrial Revolution? Would we expect the data to behave differently before and after? And it makes it so much more powerful interpreting the two parts separately when you think about having both sides. So you have both before and after.
Right. And let me do this. So I'm going to group by that variable and do two separate regression lines. And here, like this is a dramatically different story, right? You've got that line is just such a steep negative slope when you look at the context of 1200 years. And you might not want to too, because right, that's like a way you can actually manipulate viewers into thinking something is stronger than it is, right? By playing with those timescales. But if we just look at the post-industrialization, so I'm going to do two things here. One, I'm going to get rid of the pre-industrialization data, right? So I'm going to go to values and I'm going to exclude pre-industrialization. And so then we get this, and then I'm going to do another thing where I'm going to change the time scale. So instead of having the x-axis go back to the year 800, I'm going to go to 1800 and sorry, typo there, not 180, but 1800. And now we look at it, and then this is not maybe nearly as dramatic of a negative slope, but it is a pretty impressive line of best fit for a trend with something that's as variable as flowering date, right? There's just so many things that go into that. And some other background onto this and things that we might include in a final data set when we put this out on DataClassroom is that flowering date is really closely correlated with temperature too, and we don't have that in there. But this this is exactly what you'd expect in a warming climate.
Yeah, this is a good teaching opportunity about scaling axes. So that's another thing about when you're manipulating the way your graph looks, you want to tell a story, but the important story to keep in mind is you're trying to tell the story of the data. You're not trying to manipulate the data in some way to tell the story that you want it to tell. You want to be true to what the data are telling you. So in this case, not scaling the axis really small, making that slope look super dramatic to say more than it is a good lesson. And have students, so many times when graphs are reported in the news or like in pop culture, the axes are the thing that are manipulated to mislead the viewer. So there's really funny examples of that. I'm sure that's why Aaron's laughing. Yeah. But yeah, there's some crazy examples of like non-scaled axes, but encouraging students to really pay attention to the range and the scale on an axis is a great teaching opportunity.
Yeah, totally. I'm just laughing thinking about, in particular, just like bad COVID graphs that I've seen over the last 15 months or so. That that's sometimes inadvertent. Sometimes you wonder if it was intentional or not.
Yeah, dates are hard because, like you said, you converted this to, it's called like a Julian date, which is basically each day is a number. But if you put just months on an axis, it does get really confusing to think of how you would scale that.
Yep. And then the last thing I did visually, I was pleased when I searched in the data emoji library and I searched cherry blossoms, and there is a cherry blossom icon. So I put that in, but that's just purely for fun.
So yeah, now like thinking back on these two data sets, I was just thinking of the way you could kind of pair them to teach a climate change lesson with your students. The first graph or the first data set really showed pretty convincingly that the temperature is changing over time. You can't really argue with that much data and and that long a time span. And then I think this data set is really convincing for showing, to talk about the argument, are humans causing those changes? So, maybe there are natural temperature fluctuations over time, but here's a data set where we have pre-industrial revolution, post-industrial revolution. You see two very different trends and a very abrupt shift in a trend as well. So if you're you can kind of break the climate change lessons apart. And if you want to talk about anthropomorphic or human caused changes, this would be a really cool data set to use.
Yeah, that's a great idea for structuring it. I like that quite a bit. And Liz, this one leads into the data set that you know really well, because there's this kind of question of how well, sort of, one, we looked at what's the evidence for climate change, and we looked at just one particular line of evidence. Then we look at this is biological evidence, but there's also just a question of how in general do we expect living organisms to respond to climate change? Is there any way we can know about how they might respond other than just looking back at historical data? What else could we do to possibly understand that?
Yeah, I think it's a really powerful pairing of data sets to use the observational data that we just looked at. So we have these super long-term trends, but you can pair observational data with experimental data. So scientists can actually manipulate future climate change and say, okay, now we've seen this long-term trend. We have an idea of where our climate is going in the future. Let's actually set up an experiment where we just change temperature. We can hold everything else constant because you don't know what else is driving those changes. Maybe cherry blossoms are responding to changes in temperature, but maybe they're responding to something else, and you can't be sure it's temperature driving the pattern unless you just directly manipulate temperature.
Right.
All right, so I'm going to share my screen now and show an experiment that I was involved with as a grad student.
And Liz, if I could just make one comment responding to the chat while you're pulling that up. I'm going to put this in the chat to everyone. This was Elizabeth Joyner, who works at mynasadata.com, is in the audience, and she actually added a page of information about that 30-year average. So going back to that question of like, why exactly did they choose that 30-year average? How did they choose that? So I've put that in the chat, some background information, and I'll be sure to include that in the follow-up as well.
Oh, that's great. I want to know. I'm going to go read that. All right. So this is just an aerial photo showing the experiment that I'm going to talk about next. And this is an experiment taking place at the Kellogg Biological Station long-term ecological research site that I work at. And you can see 8 rings here. And these are experimental warming rings. So they're designed to change the temperature inside the rings, and they're mimicking these are in Michigan. So they're mimicking the future climate conditions in Michigan. So about, I think, 100 years in the future. So you'll see there's 8 rings here. They're randomly assigned to 2 different treatments. And I color coded them here because you can't tell the difference from the air, but they have heated treatment and then a normal or ambient or controlled treatment, where this is just normal air temperature outside. So these rings are about 3 degrees Celsius warmer. These are normal air temperature. So all the plants that are growing within these rings are basically experiencing future climate change.
Yeah, what kind of constraints do you have in setting that up? Like what kind of power source do you have available? How much maintenance do they take in the course of a season as well?
I think you'd ask, Mark Hammond is the lab technician for this lab, so you'd ask Mark and he would tell you it's a ton of work. So I think here you can see there's a control panel. We had to run electricity out to the site, and luckily I was not involved in setting up the rings. I just got to benefit and do some experiments within them. So a lot of scientists can use the same experimental setup and ask different questions once this big infrastructure is set up.
And I have a question about the setup too. With the triangular rings, I get that they were probably a lot easier to make than circles. But did you get any sort of like hot spots in the corners where you had 2 bars close to each other, or 2 heating elements?
Yeah, I'm pretty sure, again, I have to ask Mark this, but I think the triangular setup was chosen to just be easier to build than a circle and cheaper than buying curved metal. And you can see where the heating elements are placed, where they're almost circular within the
Oh, I see.
triangle.
Those are the little white things in the picture.
Yeah, so let me go to the next. Here's another picture where we can see it better.
Yeah.
Each of these things is a heating element, and it does make a pretty nice circle. So yeah, maybe you would be careful about interpreting the data. You wouldn't plant experimental plants out in this extra triangle space. You'd want to stay within the heated circle. And there are also temperature probes that go inside the experiment to see that temperature actually changed. And I'm not going to show that data now, but that's one of the first data sets your students could explore, is just, did the treatments work? So there's a data set.
I love that picture because that was not the scale I was thinking they were on. I was thinking they were quite a bit smaller. So it's cool to see that. But I always loved showing my high school students pictures of experimental setups, because it just kind of like shifts your thinking about data collection and how you run experiments when you just sort of get into this realization that like science is really creative, and figuring out how to do this sometimes takes building stuff and making your own materials, and that can be a really fun part of a high school lab course as well.
Exactly. And no experiment is perfect. You know, you kind of make decisions with the budget you have and the design that you can do. And, you know, we talked about how to best measure plants that are growing within this circle, when you really shouldn't step in it repeatedly, because you're going to trample plants, you're going to change the soil that's in the ring. So you can see all these scientists are staying outside the rings, making observations, but you try to think of all the things that could bias your results and eliminate those, and, you know, and do as simple and doable as experiment as you can possibly do.
Yeah.
So you can see this shows you pretty clearly too what was growing in the experiment. There is just the natural community of plants that were growing. And then also we planted 50 different species within the rings as well. So we had these focal plants that we can measure. And then we also had the full like background set of plants that were growing. And here you can see some scientists making measurements. So we did go in the rings because to look really closely at plants, you had to get up close sometimes. We measured a ton of different things, and I can share any of those data with you. We measured things like how much the plants were eaten, so herbivores in the plots. And then one of the measurements that they're taking here is about phenology. Again, the timing of when plants made their first flower, when they were at peak flower, just like that cherry tree data set. Okay, so that's all I want to show you about the experimental design. And then this is just a picture of the species that we're going to talk about and what this data set is focused on. It's called Dame's rocket. And this is actually a plant that's not native to Michigan. It's introduced. And so you can have some interesting conversations with your students, not only about, you know, if a plant starts to flower at a different time, are its pollinators available to pollinate it? And maybe it's losing this connection to the rest of the community if plants are responding, but pollinators aren't. But you can also talk about competition between different plant species. So some research out of our lab is looking at, do introduced or invasive species actually respond differently to climate change than native plants do? So maybe invasive plants are able to flower earlier, leaf out earlier, grow faster, and actually capture some of the resources before native plants can. And so this is there's basically, you know, if your students are interested in different questions, they could go the pollination route, they can go the, you know, flowering phenology route, or they can kind of think about invasive species and what this means.
Yeah, lots of layers of questions to climate change stuff.
Yes. All right. Now, sorry, I have the wrong tab open here. I'm going to go. Oh, I made the window too small. All right. Here is the data set that I was going to show. This is the same experiment. And now we're looking at an example of the data collected where we have ring number as our first variable. And this is 1, 2, 3 through 8. So you can see all 8 rings represented. You can see the 2 treatments, which is elevated and ambient. You can rename these whatever you like. That's most intuitive to your students, but control, treatment, heated, normal.
And Liz, I'm going to ask a naive question for the benefit of people who might be new to data science and like tidy data constructs. You have ring number marked as a categorical variable, but it is numbers. Why is that?
Yeah, I mean, we called the rings 1, 2, 3, 4, but they could have been ABC. They could have been left ring, right ring. You know, those names are actually basically just not important.
Yeah.
It's important to put the category into your data set because you'd expect that basically every plant that's growing in a particular ring is going to be more similar to plants in that ring just because they're like clumped in space. Maybe one of the rings got a little warmer than the others. So basically you can make sure that you're telling the analysis when you're doing it that you're expecting all the plants in one ring to be more similar than plants across rings.
Yeah.
So it's back to like a variability conversation with students. Like every plant is not going to behave exactly the same. You're going to see a lot of variation in the data set. What's contributing to that? You have not every plant's genetically identical. Not every ring is perfectly identical. The soil could be slightly different. And so it's basically just important to understand those sources of variation. It's not just all people messed up and when they were taking a measurement, wrote something down wrong. There's actually real variability in the data set. That's interesting.
I always love this, when you're trying to get students to write source of error in a lab report and like the number one answer, like we messed up, we screwed up, and it's like, no, there's all other sources of variation in there. It's not just that you made a mistake every time.
Yeah, exactly. That's why you replicate an experiment too. If you just did 2 rings, you wouldn't know if any differences that you saw were because of this ring's over here, this ring's in the shade, this ring's in the sun. You have to replicate it and randomize it within that setup so that you sort of try to even out all that stuff that might be adding variation to your data set. Okay, here, same with plant number. That's just a way we kept track of each individual plant. It's not really a category in the true sense of category. We have whether the plant survived the experiment, we have whether it flowered or not, and then our day of first flower. And here you can see that conversion that Erin did in the other data set where this is the date that the first flower was made by month and day. And then here it is, this 5 means 5 days after the experiment began. So we didn't start with January 1st because we just tried to capture the period of time when plants flower in a year in the summer. So yeah, this is experimental day 5, experimental day 11, 6-3, and so you can tell a lot of the plants flowered right away in the experiment. Okay, and now we'll go back and forth between, here's our table view, and we'll go into the graph view. And so the question that students are gonna first explore would be, did heating the plants cause them to flower earlier? So we have our treatment, whether it was heated or not, and the day that they made their first flower. So you put treatment on the X and day of first flower on the Y. And here are the data where you can tell the heated treatment did shift flowering to be much earlier. So if you look at it, you can see it's about 10 days earlier on average that the plants flowered. I think another kind of interesting thing to see here is not just the average of how much.
Do you want to add the average visually?
Oh, yeah,
while you're
sure.
talking about it?
Yeah, here we go. So we can go over to descriptive statistics and all right, yeah, so we'll do a boxing whisper.
You've got the median showing.
Oh, here, I like the mean. So we can see that the average shifted from about 15 to about 5 days after the experiment began. These bars are showing standard deviation. So it's capturing some of the variability of how dispersed these data are for each category. You can see heating them actually made it a little more variable too, which is interesting. And I also like looking at basically in time, these plants flowered, basically it pulled them apart from each other. There's not a lot of overlap of when the plants produce their first flower. So all the heated plants produce their flowers and then all the normal control plants produce their first flower. So if you were a pollinator, you would have seen all these heated ones first. So you could talk about what that would mean for plants with your students. And again, because this is a invasive non-native plant, you can talk about what that means for competition with native plants. So you could choose another species out of this data set, look at a native and compare the two. How did the native respond as strongly as this introduced species?
Very cool. Very cool. Yeah, it's such a clear-cut result. And then, you know, I mean, that's what you hope for in a controlled experiment, or at least a marginally controlled field experiment, you know, versus when you're looking at, you know, that natural historical phenology data. There's just so many sources of variation that affect those things. But here, you know, you can reasonably get a clear-cut result if there is a real difference caused by the temperature difference.
And yeah, when you look at, when we first looked at this data set, it was all the species mushed together, and the pattern is not as clear because not all plants do respond in the same way. Some species of plants respond to temperature, some don't. Some respond to things like moisture cues, like when rain happens in the growing season. Some species don't respond to, you know, environment at all. And so that's an interesting question to explore. If students want to get into like the natural history of different species, you can see that not everything is expected to respond the same way.
Yeah.
Cool. And so, yeah, we have these data are already up on DataClassroom, but we have more data sets and you can import those into the program. And so just, I'll have my email address on the website that you get emailed later on, and you can email me for any data sets you're interested in for this experiment.
Actually, let me put up, I'm going to put up my screen, and I'm going to show our contact information. So if any, we are coming up on our 1 hour time limit here. We definitely have some time for some questions, but if there's a question that we didn't get answered, or we didn't understand your question through the chat, please drop us a line. We'd be happy to answer that. I see in the chat, we will be sending out a recording of this, as well as links to the data sets we used, the 3 that we featured, as well as some other data sets, because there are a great number of data sets you could use to talk about climate change. So we'll try to put together ones that we have. It will be available on a website page on the DataClassroom website, which is actually a YouTube link. So if you want to share it via YouTube, you can see it on our YouTube channel as well as on our website. And again, we'll email you a direct link to that website page that has follow-up materials and the tool. I also am just going to make a plug for DataClassroom too. If you would like us to get in touch with your school to talk about a DataClassroom license, don't hesitate to reach out. But really, any question at all that you have, that's my favorite part of my job, is helping teachers work with data and ultimately helping students do more with data. So if I can be a help, let me know. And I'm pretty sure the same goes for Liz and Blake. If we can help in any way, just let us know. Any parting thoughts before we wrap up, or any last minute questions? And Nicolette, I see your comment in the chat. I will definitely be sure to follow up with you.
Oh, and Aaron, maybe we could give a plug about how we're looking for content creators.
Sorry, say that again.
And just how we're looking for teachers who'd be interested in submitting their own data sets, and then they'd be compensated for those data sets.
Yeah, we are definitely, if any of you have seen, like if I've looked at some of these lesson plans and said, I could write a good lesson plan, we would love to work with you, and we are actively recruiting people to do that. Yeah, thanks for mentioning that, Blake. So if you are interested in doing some lesson plan writing for us, we are interested in hiring you right now. So let us know if you're interested.
And Diane just dropped a good question in the chat regarding the necessity for a site license, and just say that all the features we showed today are part of the free version of DataClassroom, but to have access to the advanced features, like uploading your own data and being able to have rostering for classes and for schools, then you need a paid or school license. But our 70+ data sets are all free to use. The animated hypothesis tests and the graphing things we shared today are all part of the free features.
The only exception would be the statistical tests that we ran from the graphs. They are not, but everything else is absolutely free. So there's no reason you shouldn't be doing that with your class now. So hopefully you'll get some value out of that. And if you want more, we'd love to talk to you. Cool. All right. Well, with that, I will say thanks for joining us. I really appreciate the nice comments in the chat, and thank you. So thanks for that. We really enjoyed talking with you, and hopefully you'll sign up for session 2 in this series, and we'll see you next time.